And ladies and gentlemen, welcome once again to the Simpkins Physics Corner. Today it's scientific notation and annihilation. Let's jump into it. Scientific notation. I posted a video to Canvas for you guys to watch. It's something like 206 seconds to make you question your entire existence. And in that video clip, we observed the size of the Earth, the size of the other planets, the size of the sun, and you keep zooming out and zooming out and zooming out, and the universe is huge. There's other videos that show you how small things are in the universe as well. So when we deal with things in physics class, sometimes we're going to be talking about really tiny things, and sometimes we're going to be talking about really big things. And so in order to deal with tiny and big things, we need to use this way of writing numbers called scientific notation. So let me give you the complicated version first, and then we'll see how easy it actually is. It says used to express very small or very large numbers. That's called scientific notation. Now here's the format of the way we write the number. It's the number times 10 to the power of another number. All right, so this is going to confuse a lot of you, but don't worry. Once you see one of the numbers, it makes sense. Now, the rule here for scientific notation is the number out front of the term, all right, so the number that leads everything has to be between 1 and 10. All right, now, it can be 9.7, it can be 8.32456, it can be all kinds of numbers as long as they are between 1 and 10. Sometimes I like to say there has to be one digit to the left. I should say this again. There should be one non-zero integer to the left of the decimal point. You'll see how that works as I spell this out for you. And then n is the exponential power that we are multiplying by. All right. So if we take the number 2,300 in scientific, and we want to write it in scientific notation, this number has the implied position of the decimal all the way to the right, as all numbers do. If you're not sure where the decimal is, it's all the way on the right side. And so there it is. But the thing about the format, if we go back here, it says that there has to be the number between 1 and 10 out front. Well, what does that mean, out front? How do you get a number between 1 and 10 out of 2,300? Well, what you want to do is you want to take your decimal point and you want to start moving it until there's only one non-zero integer to the left of the decimal. There it is, 2. And so what's our answer here? 2.3 times 10 to the third power. Now, why 10 to the third? Well, because we moved 3 places. Now, here's what I want you to think about. 10 times 10 equals 100. And if you're a math person, you know you can also write 10 times 10 as 10 squared. So 10 squared is 100. Well, if I do that and I do 10 times 10 times 10, that's 10 to the third. Wow, that's not 13. It's 10 to the third. Sorry about that. It's 10 to the third power would be 10 times 10 times 10. And that equals 1,000. And I show these two examples to illustrate the point that the higher the exponent is, if it's positive, the larger the number is. So we started with a large number, 2,300. And so our final answer here has one digit to the left, or I should say one non-zero integer to the left of the decimal. And the exponent is a positive exponent because we're talking about a big number. We started with a big number, you need a positive exponent. Big numbers, positive exponents. Let's look at the opposite. This is a tiny number. Now, if big numbers have positive exponents, what kinds of exponents do you think small numbers would have? Well, let's go ahead and follow the rules. Here's the decimal. We got to move it 1, 2, 3 places. And why do we stop there? Remember the rule. There has to be one non-zero integer to the left of the decimal. So there it is, 4.7. And let's write that as scientific notation. It would be 4.7 times 10 to the negative 3 now, okay? Because when you do times 10 to the negative 3, you can ask your math teacher about negative exponents, but it basically means if I take 10 to the negative 1, that's the same as saying 1 over 10. If I take 10 to the negative 2, that's the same as saying 1 over 10 times 1 over 10, which is equal to 1 over 100. And if I multiply something by 1/100th, a fraction, it's going to get really tiny, right? So small numbers get negative exponents. So this started as a small number. Our final answer has one non-zero integer to the left of the decimal, and it has a negative exponent. All right, so that's how you go from regular numbers to scientific notation. All right, let's go the other way. If we start with scientific notation and we want to write it as standard notation, let's consider what we know. We know that positive exponents mean big numbers. So here's the question for you guys. Which way does a decimal have to go to end up having a big number? Now, if you're thinking, well, 10 to the 3, let's go to the left. What would happen if I went to the left? It would be like 0.0075. Is that a big number? No, that's a really small number. And we know positive exponents mean big numbers. So we're not going to take the decimal to the left, we're going to take it to the right. We're going to go 1, 2, 3 places to the right. Now, what do we do when we have these gaps? Well, you fill them with zeros. And so what is this looking like? Sorry, it's kind of hard to see everything there. The answer would be 7,500. Let me do it at the top here, kind of clean for you, all right? 7.5 times 10 to the third power. We would go 1, 2, 3 places over, and so our final answer would be 7,500. That's where that answer came from, all right? Positive exponents mean big numbers. What do negative exponents mean? They mean small numbers, right? So the negative exponent is going to get us a small number. It says 3, so I got to go 1, 2, 3 places to the left. Fill in any gaps with zeros. We get 0.0059. All right, so that is how we would do scientific notation, starting with standard numbers, and then this is how we go from scientific notation into the standard number. So those two reverse processes there. All right, the other rule I want you to just be familiar with, and you can always type this on your calculator, but I want you to be able to know the rules here. If you multiply terms in scientific notation, here's the rule, all right? It says coefficients, which means the number out front, are multiplied, so we multiply those two numbers together, and then exponents are added. All right, what does that mean? Well, let's take a look what that means. So it says coefficients are multiplied, so 2.2 times 5 is 11. And then the exponents are 3 and 2. Because we are multiplying these two numbers in scientific notation together, we would add their exponents, and that would add up to 5. And so what's our final answer here? It's going to be 11 times 10 to the 5th power. All right, so you can just go ahead and type in your calculator and check the answer. You'll get 11.5, or your calculator might show it in proper scientific notation, which is 1.1 times 10 to the 6. All right. The rule there is if you need to swing the decimal place to the left, then you got to bump up your exponent by 1. And if you think about that, that's just like, oh, if I divide 11 by 10, now I got to account for that extra 10, and there it is right there. That gets me to 1.1. I'm not going to be super picky about that particular part of the rule. I want you to know that when you multiply scientific notation numbers together, you multiply the coefficients and you add the exponents. All right. Well, if we multiply these scientific notation numbers with addition and multiplication, if we divide numbers in scientific notation, we're going to do similar rules, but just slightly opposite. All right, here it is. You say the coefficients are divided, so I would take those guys and divide it. So I would do 6 divided by 2, that gets me 3. And then I would subtract the exponents. So it would be 3 minus 2. That would be 1. How do you combine this to your final answer? 3 times 10 to the 1 power, all right, which is really just 30, all right? But that's how you'd write it in scientific notation. So are you able to use a calculator? Yes. Do I want you to also be familiar with the rules for multiplication and division? Yes. I'm not going to give you crazy hard ones. I just want you to be familiar. When you multiply numbers with scientific notation, you multiply the coefficients, you add the exponents. When you divide numbers in scientific notation, you divide the coefficients and subtract the exponents. And we'll see some examples of that in just a second. All right, so what I want you guys to do right now at this point is pause the video, go download the document that I posted to Canvas for you with this practice work, and I would like you to try some of these out. I'd like you to try some of these out. So go right now, download the packet, try some of these out, and then come back to this video and press play, and we'll see what the answers are. All right, so if you did some of the practice, you can check your work here. Give me a shout if you don't like any of these. Oh, I already don't like one of those. Wow, who did that one? That's terrible. All right. This one is times 10 to the 8, so this should be 5, 1, 3, 4, and then 1, 2, 3, 4, 5 zeros, which would look like that. That'd be a really big number. Okay. Just a quick glance. I'm liking the rest of those. And the ones down at the bottom, I'm going to assume are correct too. Give me a shout if they're not, and I'll fix the video for you guys. But I'd like you to check your work after doing that practice until you feel comfortable with the scientific notation. All right. Barrier Sensei. Now we got Rex Kwando because I'm really excited to annihilate some things. We're going to annihilate it. Let's see what that looks like. Now, when you are in math class, if you were multiplying 2/3 times 3/4, how would you do that? Well, some people are like, well, you got to do 2 times 3, and that's 6. And you got to do 3 times 4, and that's 12. And then I guess you'd simplify it, and it would be 1/2, right? You could do it that way, all right? But look at this. If you multiply two fractions together, right, and you have the same term on the top of one of those fractions as is on the bottom of another one of those fractions, for example, if I have 3 and 3, I have a question for you guys. What is the numerical answer for 3 divided by 3? If you said 1, you're correct. And what happens when you multiply something by 1? its value doesn't change. So what does that mean? That means if I multiply two fractions together, and this one has a 3 and that one has a 3, you can annihilate them. Rex Quanto! You can annihilate them. See, in math, you may have heard, you cancel the terms out. Oh, that's so fun. That's so great. No, we don't cancel terms out here. All right, we annihilate them. So we annihilate them. Let's look at another example here. We annihilate those and go to the next one. All right, remember the rule. If you multiply fractions together, there's the same term on the top of one and the bottom of another, you can annihilate them. All right, so the 3's get annihilated, and the 4's get annihilated. And then what do? You gather up the survivors of all of the annihilation carnage, and the answer to that is 2/7. Wow, that's a neat trick, Mr. Simpkins. Gee willikers, yeah, it is. All right, let's look at another one. What if you have all these fractions multiplied together? Well, you got a 2 on the top, 2 on the bottom. Annihilate them. You got a 3 on the top, 3 on the bottom. Annihilate them. You got a 4. You got a 1. Well, that just kind of goes away there. And you have a 4 on the top, 4 on the bottom. Annihilate them. And so what's your answer? It's 1. So all that crazy math that we could have done, and the answer is just 1. Fantastic. Now, Mr. Simpkins is about to get real crazy up in here, right? Because we are annihilating numbers. What if we have variables? What if there's a y on the top of one fraction multiplied by another fraction with a y on the bottom? Guess what you can do? Rex Quando! You can annihilate him. Oh man, wow, my animations are anyway. Annihilate him like that. And the answer to this would be x/z. Oh, that's fantastic. It makes me so excited. Whoa, how about this one? Well, I see a x on the top and an x on the bottom. Annihilate him. I see a y on the top and a y on the bottom. Annihilate him. I see an a on the top and an a on the bottom. Annihilate him. And the answer here is z. Wow, that was easy. What about this craziness? Sorry for all you PETA folks out there, but I have to just keep going with this one, because if you have a frog on the top and the frog on the bottom, annihilate him. If you have a bear on the top and the bear on the bottom, annihilate him. And the answer is dogs over ants. What does this have to do with physics, Mr. Simpkins? Well, if we convert units, we can use the strategy of annihilation to do so quite easily. All right, let me give you an example. If I want to convert 4.5 meters to centimeters, all right, I could use the King Henry doesn't usually drink chocolate milk stepladder and do it that way, or I could annihilate, because I like annihilating things. So here's how it goes, all right? I'm going to multiply by a fraction, and we know that if the meters are on the top of the first term, where do they need to be in the next term to annihilate them? Answer, the bottom, right? Because if there's the same term on the top and bottom of two fractions multiplied together, they annihilate. Rex Kondo. All right, and so I want to go to centimeters. So you put the unit that you want to go to on the other side of the fraction, whether the top or the bottom, the numerator or the denominator. Now, the caveat here is you're not allowed to just multiply a number by something randomly. You are, however, allowed to multiply a number by 1, because that doesn't change its value, right? And so when you set up the next fraction, the amount of stuff on the top has to be equal to the amount of stuff on the bottom. And if I know something about centimeters, I know that there's 100 centimeters in 1 meter. If I said, hey, can you draw me a 100 centimeter line? And then I said, hey, can you draw me a 1 meter line? They would be the same length. So there's the same amount of stuff on the top and bottom of this fraction. That's why that's a legit math move. And here we can annihilate the meters, all right, because there they are. And then when we gather up the survivors, we see, what do we have left? 4.5 times 100. All right, so that's going to be 450. It's going to be 450. And the centimeters survived. And of course, the 1 survived, but that's kind of boring. So our answer here is 450 centimeters. That's a pretty straightforward, pretty easy one. All right, how about this one? 1 year equals how many seconds? 1 year equals how many seconds? So we'll set it up like this. 1 year up here, I'm going to multiply by a fraction. Now remember, if years are on the top, where should I put them in the next fraction to get them set up for annihilation? On the bottom. All right, so there it is. The year goes on the bottom. Now, if you are a musical fan, you will know how many minutes are in a year. All right. Minutes. There are 525,600 minutes. So a little bit like that. Oh, 600. There you go. And that's from the musical Rent, if you know that one. All right. And so I just went from minutes to years. There's 525,600 minutes in a year. And then that annihilates the years. And I'm almost there to get to seconds. Minutes are on the top, so where should they show up in the next fraction? On the bottom. And I want to go into seconds, so you put the unit that you're aiming for on the other side of the fraction. And I know that there are 1 minute is going to be equal to 60 seconds. You have to have an equivalent amount of stuff on the top and bottom. And I'll leave it to you guys to calculate what that number is. All you have to do to get the final answer is multiply 60 times 525,600, and you would get the answer for seconds, because the minutes annihilate. Last one. Oh, we're coming down the end of the clock here. 25 kilometers per hour. All right, so you want to set it up as a fraction, and this is where things get a little crazy, so follow with me here. Kilometers are on the top, put them on the bottom. Kilometers is sounding like meters, kilometers, and they both measure the same thing, and 1 kilometer is equal to 1,000 meters. Then I'm going to multiply by another fraction here, Hours are on the bottom, so I want them to show up here on the top. 1 hour is how many seconds? Be careful, don't speak too soon, because it would be 3,600 seconds for that hour. All right, sorry, I'm running short for time, but check it out. We annihilated the kilometers with kilometers. We annihilated the hours with hours. We gathered the survivors. We multiplied them together, and our final answer is going to be 6.94 meters per second. Check out the worksheet and have some